In this video, we're going to be studying the concepts and calculations involved in weak acids. So the most important thing to remember is that weak acids do not ionize completely in water. So weak acids always have an equilibrium with their unionized form. So effectively what we're going to do is we're going to use familiar methods to determine the concentration of H+ ions, OH ions, pH, and POH, and then find K values for these compounds. So just to review, a weak acid is a compound that only partially ionizes in water to produce protons. So a way of looking at this is we could look at acetic acid, and we could say that CH3COOH, okay, is in equilibrium with CH3COO acetate and protons. All right, but recall that protons don't exist on their own. Another more accurate way of writing that equation is acetic acid is in equilibrium with liquid water. Acetic acid will donate a proton to water, making it a Bronsted-Lowry acid. And then we have the equilibrium of acetate, which is its conjugate base, and hydronium, which is the conjugate acid in this Bronsted-Lowry acid-base pairing. My preference is to use the second equation because it really highlights the Bronsted-Lowry behavior of acids in that acetic acid donates the proton to water. We can use percent ionization, which is a method that allows us to calculate concentrations, and percent ionization is given as percent H+ or percent H3O+ is equal to the concentration of H+ or H3O+ over the initial concentration of the acid times 100%. Okay. Another way of shortening that is P is equal to H+ over HAI times 100%. Now that's for an acid. If we wanted to do this for a weak base, I'll just quickly show you that. That's P, and that's OH minus over the concentration of the initial concentration of your weak base times 100%. Another method to determine concentrations in pH is using the equilibrium constant method via an ICE table. So in this example right here, we're going to show you both methods. So percent reaction with water, it says percent dissociation. In this case, it's ionization because it's producing ions. So ionization, let's just correct that. So the percent reaction is different with different acid concentrations, thus the data is not readily available. So over here in this question, they give you an initial concentration of your acid. That's your initial concentration of the acid. They give you the percent ionization, and they want you to determine the pH. So if I want to find the pH, I'm just going to quickly write the formula here. pH is equal to negative log H+ or H3O+. So I need to use this formula up here to determine my H+ so that I can determine the pH. So I'll start by stating the formula. P is equal to H+ over the initial concentration of acid times 100% So P I know is 2.5%, but what I'm going to do is I'm going to switch that to a decimal and get rid of the 100%. So 0.025, that's 2.5% as a decimal, is equal to H plus, which is what I'm trying to look for, over 0.100, and that's moles per liter. Isolating for H plus, I get 0.0025 molar for H plus. And then from there, to find the pH, I do the negative log of my H plus value. And so that's negative log of 0.0025 molar, which is then equal to approximately 2.60. Okay, so that is determining the pH using a percent ionization and an initial concentration of the acid. But we can also find the pH using a Ka value, or an equilibrium ice table. And so what we do is we set up the equilibrium equation as we saw previously. Again, my preference is to use the acid reacting with water so that we can show that it is donating a proton. So as you can see here, the acetic acid donates a proton to the water, and again I can just quickly show you that. So acetic acid is your acid. Set up my ice table, and recall that since water is a liquid, I do not have to calculate its concentration because its concentration is a constant. So I'm only going to be calculating the concentration of the other species present here. I have my initial concentration of 0.1, so 0.100 molar, and there are initially no concentrations of acetate and hydronium. So I know it's going to shift to the right, so plus x, minus x, and then I have 0.100 minus x, and x. Okay. Set up my K equation, or my equilibrium law, K sub A, and I use the subscript A to indicate that this is an equilibrium involving an acid. So I have my acetate concentration at equilibrium times my hydronium concentration at equilibrium, so at equilibrium there, and then I have my acetic acid concentration at equilibrium, which is right here. I insert the values and I get 6.5 times 10 to the negative 5 is equal to x times x all over 0.100 minus x. So I can go ahead and solve this, or let's just simplify it first. This is easy enough to solve because it just produces a quadratic, so you can bring everything to one side and use the quadratic formula. Alternatively though, we can check the 100 rule and see if we can simplify this a little bit. So the initial concentration of the acid is 0.10 divided by the Ka value, which is 6.5 times 10 to the negative 5, and check to see if that's greater than 100. And when you put that into your calculator, you will find in fact that it is greater than 100. So we can perform the following simplification. We can say assume that 0.1 minus x is approximately equal to just 0.100. We make that simplification because the Ka is so small. We know that the shift to the right will be quite small, and because the shift to the right is very small, this x value will be small in comparison to the 0.1. So subtracting a very small value from that 0.1 is negligible or insignificant. So we can just go ahead now and continue our calculation with our simplification. So 6.5 times 10 to the negative 5 is equal to x squared all over 0.100 based on my assumption. So I'll put a little dot over the equal sign there to indicate that it is an approximation. I bring this over, the 0.1 over to this side, so 6.5 times 10 to the negative 6 is approximately equal to x squared. And then when I square root both sides, I'm going to end up with x is equal to like plus or minus 2.55 times 10 to the negative 3, which I can immediately discard the negative value because I cannot have negative concentration. So I'm only going to take the positive value. Then I perform a pH calculation, which is, and this by the way is equal to your H3O plus concentration at equilibrium. So negative log H3O plus pH is equal to 2.6. Well, I'll put in the value 2.55 times 10 to the negative 3, which is equal to 2.6. Okay, and just for just to be complete, I'm going to put dots over the arrow, or sorry, dots over the equal signs, except for the general formula there. Okay. All right, so we've just gone over two ways to calculate pH using a percent ionization calculation and also using an ice table. This second method here is a fairly standard way of calculating pHs or Ka values, so it's in your best interest to become quite familiar with this method right here. Moving on. A solution containing HSO3 from an NaHSO3 solution has a pH of 5.20. What concentration of HSO3 is dissolved in this solution? Okay, so what we're going to do is, first thing I'm going to see is that this HSO3 or bisulfite is coming from a sodium bisulfite solution. So the first thing that happens is you have a dissociation equation. In which your sodium bisulfite dissociates into sodium ions and bisulfite ions. We will not consider the sodium ions because they do not participate in the acid equilibrium. So the sodium ions dissociate and then they just kind of float around. So they're actually spectator ions. This is the important species that affects the pH of the solution, and we'll see why in a second. We're going to use our equilibrium equation and an ice table. So we take the species that's affecting the pH, HSO3 minus, and I know that this one's affecting the pH because it effectively tells me in the question that this is what we're looking at, right? And even gives you a Ka value for that species. Again, I'm going to react it with water so that I can show that it is donating a proton, and I get SO3 2 negative, which is its conjugate base, and H3O plus. And just to quickly show you, it's going to be donating that H to H2O. I'll now make an ice chart. And my initial concentration of HSO3, I don't have that. That's what I'm trying to find out. So I'm just going to put it in as Y. That's my initial concentration. I don't know what it is. And I have no initial values of sulfite or H3O+. So I know the equilibrium will shift right. And at equilibrium, I will have y minus x. And over here, I will have x, and I'll have x. I'll set up an equilibrium equation here. So K is, or rather Ka is equal to the sulfite concentration at equilibrium, the hydronium concentration at equilibrium over the bisulfite concentration at equilibrium. Now, since I was given the pH of 5.20, I actually have this X value. Okay, so this X value is the concentration of H3O+ at equilibrium, and I know that the concentration of H3O+ or H+ is just equal to 10 to the negative pH. So I have this X value. So that's 10 to the negative 5.2, which will be equal to 6.3 times 10 to the negative 6. 6.31 times 10 to the negative 6. So I, in fact, have this X value. So I'll only have to solve for the Y value here. So I'm going to go ahead and I'll restate my Ka right here. So the Ka value was, therefore, 1.0 times 10 to the negative 7, that's my Ka value for this, is equal to SO3 2 minus is X, right? But X is just equal to this value right here. So I'll have 6.31 times 10 to the negative 6. Okay, and then 6.31 times 10 to the negative 6 here as well, all over bracket y minus 6.31 times 10 to the negative 6. Okay, I'm going to isolate for y, and to do so, what I'm going to do is I'm going to start simplifying. So 1.0 times 10 to the negative 7 is equal to 6.31 times 10 to the negative 6 squared all over y minus 6.31 times 10 to the negative 6. I'm going to flip both sides of the equation. So 1 over 1.0 times 10 to the negative 7 is equal to y minus 6.31 times 10 to the negative 6 all over 6.31 times 10 to the negative 6 squared. I will multiply both sides by 6.31 times 10 to the negative 6 squared. And then I'll end up with a value that will, just give me a second. So on this left side here, what I will do is I get 0.000398 is equal to y minus 6.31 times 10 to the negative 6, and then I find that y by adding by adding 6.31 times 10 to the negative 6 on both sides, I get y is equal to 4.03 times 10 to the negative 4, which was my original concentration, or my initial concentration of HSO3 minus, right? So that's my initial concentration of bisulfite, and knowing that there is one bisulfite for every one sodium bisulfite that dissolved, I had to dissolve a concentration of 4.03 times 10 to the negative 4 molar sodium bisulfite in order to produce this pH. Okay. So again, we don't consider, or we don't look at the concentration of sodium because it doesn't participate in the acid equilibrium. So we just call it a spectator ion, but we can't get the bisulfite without dissolving sodium bisulfite. So the sodium is necessary to obtain the bisulfite, which produces the pH that we're looking for. Okay, substantial amount of math over here, but once you've set this part up over here, it's easy enough to just isolate for Y. Okay, finally, a polyprotic acid has more than one proton, so poly meaning many, and protic meaning protons, right? So for example, if we look at phosphoric acid, there are 3 Ka values. We've got 7.1 times 10 to the negative 3. So that is for phosphoric acid donating its first proton to water. Okay, they don't all come off at the same time. So that's donating one proton to water and causing this equilibrium to happen. As we can see here, 7.1 times 10 to the negative 3. It's not a very high value, so this is definitely a weak acid. Now, once it's donated one proton, it will continue to donate other protons, right? So it still has 2 protons left to give. So let's write that equilibrium. So again here, it has another proton that it is able to give. Let's just show we've got this one proton being donated, another proton being donated. But if we take a look at this, 10 to the negative 6, well, that's very small, right? And this is actually 100,000 times smaller than the donation of the first proton. So the donation of the second proton barely happens. And if we look over here, the donation of the third proton, well, again, that's 10 to the negative 13. That also doesn't really happen very much. So if we consider phosphoric acid, effectively, the only donation of protons is the first one, right? We can assume that phosphoric acid only really donates one proton because subsequent donations of protons have very, very small Ka values, so they're insignificant. So what we would say is that these are effectively insignificant. Because the Ka values are incredibly small, there will not be a large shift to the right. So we make a generalization. In general, for any polyprotic acid, we assume that all of the first H plus will be removed from the H3A acid molecules at equilibrium before you get any of the second or third donations. So when we calculate the pH for polyprotic acids, we can obtain the pH by calculating strictly off the basis of Ka1. So when we go to do our ice table, we are only going to use Ka1 because it is so much larger than the other, Ka1, because it is so much larger than the other Kas. So we're going to use an ice table, Ka1, and we're going to ignore Ka2 and Ka3. So we'll do a quick example of this. So say we have sulfurous acid, H2SO3, and we've got Ka1, which is 1.5 times 10 to the negative 2, and Ka2, which is 1.0 times 10 to the negative 7. So as you can see, this is the value that we are going to use, right? Because this is significantly smaller. So write the chemical equations to correspond with the 2 Ka values. All right, so if we do this one, H2SO3, donating a proton to water, and we get HSO3 minus plus H3O plus, and my Ka1 is equal to 1.5 times 10 to the negative 2. Subsequently, HSO3 minus plus water will form sulfite and hydronium, but at a very small Ka value. So if I wanted to find the pH of this solution, all I'm going to do is I'm going to set up an ice table using the first equation. So H2SO3 plus H2O forms HSO3 minus plus H3O plus. Okay. This right here is 0.05. That's 0 and that's 0. This is minus x. This is plus x plus x. This is 0.05 minus x. And this is x and x. Okay. I'll set up my Ka expression. So Ka, and I'm just going to use Ka1, is equal to HSO3 minus H3O plus all over H2SO3, and this is at equilibrium. Okay, so my Ka1 value is 1.5 times 10 to the negative 2, which is equal to x squared all over 0.05 minus x. In this example, I cannot use the 100 rule, so I will have to use the quadratic formula. I'll have to expand and use quadratic formula, so I'll just write that over here. Expand and use quadratic formula. And then I will have x is equal to approximately 0.0210 molar. So the pH is then equal to the negative log of that x value, which is your equilibrium concentration of H3O plus, 0.0210, and that is approximately equal to 1.68. Right, and so just so that we're clear, that's your equilibrium concentration of H3O plus at equilibrium. All right, so just reviewing, what we did is we set up an ice table for the first donation of the proton. We assumed that the second donation was negligible, so we're only looking at the pH caused by the first donation. So we set up our ice table. We insert it into the equilibrium law for the acid, and then we solve for x by using the quadratic formula because the 100 rule would not work here. I'm also assuming that you're going to throw out the value that is not that does not work in the context of this question, and so this is the value that does work. That's your hydronium concentration at equilibrium. You put that into the pH, and then you get your pH for this question. Great. Thanks for watching.